Amazing. So thank you so much for inviting me. I'm excited to be here and talk about learning to discover at test time or TTT Discover. This is like paper that is going to be present at ICML in a couple of weeks. It's a joint work with people at Stanford, NVIDIA, the Astra Institute, and UC San Diego. So first thing first, about me, I'm a senior ML scientist at Together AI. I was formerly at Open Evidence and a postdoc at Stanford. I mainly work on self-improving agents and scientific discovery. And I have a bunch of things that I want to mention before going on, which is stuff we've been doing in the last couple of months. One is like this Agent for Science conference, which was the first event in which we asked AI agent to write and review papers. It was an interesting experiment to see what would science look like if agents were first-class citizens of this world. And another thing we have done recently on the more higher democratization of agentic research is this idea of Einstein Arena, which is very close to Malt's book, if you think about it, is this a social network with a giant leaderboard in which agents can work together to solve open math problems. We found that agents have been able to solve some of these problems efficiently. So it's an interesting kind of thing that I wanted to mention. Cool. Let me move to the paper. I have a section that is going to be the paper in 2 minutes, which is going to summarize everything that I think is important regarding this paper and is the one that contains the most somehow take-home messages. So first thing first, I'm sure like this has been the core of the entire conference, but to mention this again, we talk about discovery problems, and a way to describe discovery problems is to get artifacts and improving them. An example of this is like you have a slow kernel, you for any CUDA GPU, you want to improve the kernel, so you send this to a language model and you obtain a new kernel that you hope is fast than the previous kernel. So there is this concept of like discovering new objects that somehow bring you to a new state-of-the-art solution. So these problems all have in common, or at least like the one we approach in TTT-Discover, have in common that they are verifiable. So there exists a verifier that gives you an objective way of looking at this object and also offer a continuous reward. This can be GPU kernel optimization, for example, so finding new kernels that are faster than past kernels. It can be like finding new mathematical bounds for some quantity of interest or finding new algorithm in this context for single cell denoising, which is a possible example of algorithm. So most of these tasks, if not all of them, are out of distribution. We have now trained on the entirety of the recorded knowledge. The question is like, how do we approach these new problems for which there is no answer out there? How do we do things in an out of distribution manner? These are novel by definition. So models trained on average performing on general data, they might not be good at solving this. What with TTT-Discover, we try to somehow argue is that what you should do is that you should train at test time. You should take the problem of interest and you should let the language model, the agent or whatever, interact with the problem in a reinforcement learning manner on the problem itself and improve over time. So there are some things that we say we can only learn once we are actually trying to solve the problem itself or at test time, which is the general claim of this part. So the other thing we do here is that like we work on one single target. So in this context, we assume that discovery is a single objective, finding the best solution for a specific problem, which is finding a new faster kernel for gem multiplication. TT-Discover approaches this by creating environments in which there is only one problem and the policy is not the objective anymore. We just work on this problem itself. And we train on tests on the same exact problem, trying to hill climb toward the possible best solution. Also, there is this behavior in reinforcement learning that tend to be average seeking. So standard reinforcement learning tend to maximize the average reward. What instead we want to do with TT-Discover is that we need only one exceptional result. So we should actually optimize for a maximum reward, not the minimum reward. So this is going to change the optimization function we use in our reinforcement learning strategy. So we want to find the best artifact, and the policy we train does not need to generalize. In fact, once we train the policy, we can throw it away, and we should be just left with a good artifact. So to summarize, TTT-Discover is going to be test time reinforcement learning on one single problem for which we're going to optimize for a maximum reward. And there is a bunch of very important related work from which we, of course, have been inspired from. Cool. Let's start with a more structured part. So the formalism of discovery problems. How do we define discovery problems? And we define them as those problems in which even small improvement carry real weight that can somehow push the frontier. And again, math, GPU kernels, algorithm design are all good examples of this kind of problems. When we think about the discovery problems, a possible formalization kind of look like this, and this is inspired from the AlphaEvolve one. So given a problem description D, we cast discovery as a search over a set of candidates. So we have a set of states, which could be like a set of like GPU kernels, math construction, or an algorithm. We have actions, so the model is gonna output reasoning tokens followed by code that we're gonna use to produce the state. We have a transition function that is gonna use to take that code and generate a state. And finally, we have a reward for kernel, for example, could be 1 divided by the runtime, or for a new mathematical bound can be 1 divided by the bound, depending if this is a lower or an upper bound. We say that we got a discovery if we find a state in which the reward we get from that state is larger than the reward we got from the state in the state of the art. So this is how we define the actual discovery in this context. Cool. How many methods work? Or like, let's go to the search part of this discussion. And many methods, or like the most basic method to do this kind of discovery is best of n. You just take a problem, you sample a bunch of times from a language model, you have a few candidates, you score all the candidates, and then this is your best solution. So again, your problem is writing a kernel, you sample n kernel from the candidates, you evaluate them, and then you have your fastest kernel that you could find with this model. This is problematic right now because like the horizon is pretty short because it's one step. But what you can do in this context is that like you can extend the horizon. So if this is your prompt for best of n, optimize this GPU kernel, one thing you can do is that you can add stateful prompts. So this new prompt is going to be optimize this GPU kernel, but you also add the previous attempt, which could be this kernel, for example, so that like the model can use this to perfect the previous kernel in an evolutionary manner, as we saw in many of the models that have, or the system that have been introduced in the state of the art. So the model is going to build on its own best work and is going to extend this horizon just by looking at the previous attempts. And this is what it would look like in general. You will have a problem, you will have your buffer of states, you will sample from the buffer and generate new candidates. All these candidates are going to be scored. You're going to get a new best solution. This is going to go back into the buffer. And the more time you do this, hopefully you're going to extend your horizon and you're going to get a better version of your target artifact. This is how I like to think about a lot of like these system that use these evolutionary strategies. And this is in general what I refer to as search methods. The most relevant one, or like one of the most successful, as I'm sure you have seen a bunch of time during this conference, is AlphaEvolve, which was one of the first big approaches to show that like LLM-driven search can actually make real discovery. And of course, like a lot of our work builds directly on this insight. What we kind of want to change here is that like there is one big limitation. Search is going to improve the candidates, but the model never learns. The policy is actually frozen, and it never internalizes what it actually discovers. But if you think about how humans learn, this is a little bit different. So if you go back to like when you were doing textbook problems, you might remember that those never looked like the exact things you were learning during the lecture or during class time. There's always something different about textbook problem. They require attempts, they require you to approach the problem in a few different ways. And the programs comes actually from failing, realizing what fails, and improving your own approach in spite of failures, learning what works and what doesn't work. So you cannot solve this by first attempt intuition. You need to learn how to approach this problem in practice. And you could say that in a general level, the human learning loop could look like this. You have a hard problem, you do some attempts, you evaluate the state of the solutions, you refine your strategy, you do these a couple of times, and eventually, hopefully, you get to some kind of breakthrough that is going to be your actual result. So the question now is, if humans improve by learning from every attempt, what if we actually make our discovery system do the same thing? And this is where TTT-Discover comes in. And to be clear, I think TTT-Discover is very simple in its conceptual part. It should be very easy to understand what TTT-Discover is doing because it's just like a way of like looking at how to approach this kind of problems. So as a recap, we are going to approach one problem at a time. We're going to train and test on the same problem. Our goal is hill climb on that very specific problem. And for us, the policy is kind of disposable. Only the best delivered solution is going to matter. You could argue that like you could do this with actual simple naive reinforcement learning, but naive reinforcement learning has a bunch of problems. And what the intuition that I would like to give you is that like we want to look at what the best rollout do at every step, and we want to make those best rollouts much more likely, not everything more likely on average. So the general idea is that like naive reinforcement learning tends to optimize for average, but we actually need the maximum. There is this idea of like there is generally short horizon, so we need some kind of buffering it to include the states, but we need to balance exploration exploitation as always in this kind of setting. But this balance has to be looked from a point of view of this max seeking behavior or like this discovery based behavior. So what does TT-Discover change in practice is if the problem is optimizing for the average reward, we're going to use the entropic objective that is going to favor the maximum. If the problem is that the exploration tend to collapse, we're going to use the packed style reused that is very inspired from the literature with one modification to introduce some kind of more balanced search. I'm not going to spend too much time on the entropic objective itself. The general idea is that like we want to change the objective in such a way that it rewards more high reward somehow actions. And I have an image that is going to show this in a more concrete way. But the idea is that like we have this beta parameter that is going to regulate how much weight is going to be put on the most successful action. And if this is like the standard setting in which like you have a more common weighting scheme, the higher the higher value you assign to beta, the more weight you're going to move on the action that like gives you more reward. It's a very simple idea of like redistributing the weights of the reward to the most successful actions, or like the one that brings you closer to whatever goal you are trying to achieve. The other thing we do is that like we have this pact inspired rule, which is taken from the literature with one minor change. The idea is like we want to explore a good state and explore unvisited states, but this is probably best shown with an actual example. So let's say that like we start with the Tor one and we have a seed prompt and we generate 5 candidates with different score. The question is which solution should we expand next? And one idea is like we start expanding the most successful solution. So we use this scoring function, which is the common one. This is our exploitation bonus, and this is the exploration one, where Q of S is the best child reward, not the average child reward, which is a difference with the state of the art, plus this exploration bonus for the undervisited states. So it turns to what happens, we might expand K3, and we got this list of 5 new states. So now we have 10 states in the buffer. The question is, which states are we gonna keep? Are we gonna select as a next state to work on? If we compute QK3, the value of QK3 is gonna jump to 0.86 because, like as we said, Q of S is the best child reward. So one great child is gonna lift the entire lineage of the scores. And what happens here is that like due to the fact that like we are also waiting for the exploration bonus, we're gonna select K7 because it's a brand new state. But the idea is that like over the process, we are gonna balance this idea of like sampling new states that are very valuable, K7, but also at a certain point, we might wanna go back to sample from K3, which was a very good original state. So we are going to stay open to explore the possible past and use those effective states. So just to see what the loop would look like entirely, let's say the goal is like to discover a new soda kernel for the Trimble. What we do is that like we ask the model to write a fast write on Trimble kernel. We sample the rollouts. We have some value. We add the states we got from to the buffer. Then we get the best states. We put these into the prompt. We sample rollouts and so on and so forth. And then we do all the gradient updates and we try to get to the best possible result. Let me move a sec to the implementation. For all the experiments we have run, we've been using GPT OSS 120B. So open model, everything is open. It's trained on Tinker, which is a very good way of abstracting infrastructure. So you actually don't need to own any GPUs to do this. You can use online infrastructure. The cost is around $500 per problem for the problem we've been tested, which is a pretty good price for making novel discoveries. This is our code that we published a couple of months ago. It should be very easy to add any new task to this setting. You just define a reward function, you define your environment, and basically use our infrastructure to just run the training. It should be almost seamless to just run these on your own tasks. This is an example of possible prompt that we used, which is the standard persona setting. You are an expert software developer. There are the states, as I was mentioning. So the model knows the best score. The model knows the best state, so the actual construction for a mathematical problem, for example. And the model also knows the previous code, and the model is asked to like improve this code, and so on and so forth. Cool. The experiments. This is a very important part because it's very hard to evaluate these things because you don't know what the model knows and what not. The idea, we try to focus on leaderboard. So um, settings in which we know that there are open problems. We know that humans also try to solve those problems. We tackle this kind of hard problem that are also kind of outside our domain of expertise. And so for each problem, we ask the an expert reviewer to review our results to ensure we're actually doing the right thing. So we have four domains. I'm going to quickly cover two domains: GPU kernels and mathematics. Algorithm design and biology are actually in the paper. So let me show the Trimble optimization, which I think is fun. This is an example of the search baseline on the GPU mode Trimble competition kernel runtime for an H100. So we run best of 25K. So we sample 25K samples, and we look at how fast these examples are. And this is the distribution. You can see that this is the best kernel for GPT-OSS without any training, and you see it's very far from the best humans. So, oops, sorry. What we do is that like we try TTT-Discover, so we train exactly on Trimble, and you look at like, if you look at like the time zero is the same model, so there is no difference in the distribution. But the more you go with the training, the more the model learns to do the right thing. So at step 10, the model has learned to apply mixed precision. At step 25 is fusing core operation, and at step 50 is actually doing some kind of deeper fusion. So we train these with runtime, we train on H100 only, we evaluate on all the GPUs for the GPU mode leaderboard. And what you can see is that like we actually get very consistent scores, sometimes up to 50% faster, despite training only on one H100. So on all of these, we are actually beat all the human result up to the day we tested this on. Another experiment we do is on standard mathematical open problems. I'm not going to spend too much time on these because these are very are particular problems that are related to math. But it is that like we approach this problem that have also been tested by AlphaEvolve, and our results seem to show that like we can improve significantly over AlphaEvolve with an open source models. I have some plots here to show that like the differences, like the different bounds we have tested. I'm sure that like most of these might be known because these are now very standard in the actual literature. Cool. Let me quickly wrap up this presentation. The main summary of this is like we do test time reinforcement learning on one problem and optimize for a maximum reward. In standard RL, the policy is the end. Here, the policy is merely a means. We only need a single best solution, and this is why we optimize one problem for the maximum reward with the entropic objective and the packed reuse rule we mentioned. Everything here is scientific discovery with open models, and we just use GPTOSS. Everything is public, and so you can also use this and repeat this. These are like some of the results we got versus the previous state-of-the-art results. And yeah, thank you very much for inviting me. I'm happy to answer questions, or like if anyone is interested in this topic, feel free to reach out either on LinkedIn or via email or to chat a bit about this problem.
Thank you very much, Federico, for the talk. It was really nice. I think we have time for a few questions. There's
Cool.
one from Daniela. So TTT-Discover shows that a model can significantly shift its behavior distribution during inference on a single problem. From a security perspective, if an adversary could influence the reward signal at test time, TTT could become an attack vector rather than the discovery tool. And from the detection side, what signals would you expect to be observable in the model's output distribution that would indicate TTT-style adaptation is happening, as opposed to a frozen model doing standard search?
Yeah, that's a good question. I'm not too familiar with this literature. I would say that like yes, an adversary could definitely influence the model to change its behavior. I would say this is common to any kind of fine-tuning systems. You can already see from the sampling distribution that the model behaves differently. So you could somehow detect that, but I'm not really sure what would be the right example for the more security related setting.
Okay, maybe now a question of my own related to the work. So you mentioned that the cost was around $500 per problem, right? Did you ever do an experiment regarding how transferable this knowledge is? Like, for instance, if you do RL testing, RL training for a narrow problem, maybe can you expect it to be better at problems from additive combinatorics? Can you transfer this to other problems to make it maybe more accessible? Because maybe the average person doesn't have $500 per problem, but they might have $500 for a single problem and might hope to use this in other problems.
Yeah, that's a very good question. So we didn't test that directly, but we have some experiments in the paper that show that like these models do not lose all the knowledge they originally have. Since we are doing low rank adaptation, the model still can use some of the original knowledge. So I'm sure that like some of these could be used, some of like the learned knowledge can be used on other problems, but this would be like a more consistent setup to actually be evaluated. So I'm sure that like the model learns something and also doesn't forget everything, but I would need more practical experiment for this. Yeah.
Okay, thank you very much again. It was really nice talk.